you a couple problems that I've been having some trouble on.
Okay.
So I have a test tomorrow, and so the subjects that my tests are on is finding limits graphically and numerically, and then it's there's like a preview to calculus section, which was on secant lines, finding the slope of secant line.
Slope
Yeah.
of tangent line is almost the definition of differential calculus.
Okay.
Really,
Yeah, I didn't really get that. So,
it would,
um,
if you could only use 3 or 4 words to describe it, it's the instantaneous rate of change.
mhm.
That turns out to be the slope of the tangent line. So,
Okay.
but
Super.
let's
So,
see. You want to? Shall I take a look at the ones you sent me?
yeah.
Let's
Mhm.
start there,
Yeah.
because I also have some that
Okay,
look
perfect.
like.
Because I'm really stressed about the test tomorrow. So,
Okay, you asked me to put together some problems, so we could
yeah.
do these, but it's better to do the ones that you have. So let's see if I can bring those up. All right, starting from the left. Now, oh.
Yeah,
All
that's
right.
the first.
Yeah. Well, let me say a few things about this. This is the delta epsilon definition of limit,
Mhm.
which is this wasn't even derived until about 100 years ago. This was the last thing that came about. This is a hardcore mathematical proof as to how you really define a limit. And
Okay.
it is actually a subject, in the words of Saul Kahn. You know who Saul Kahn is?
Yeah, Khan Academy, right?
Yep. In the words of
Yeah.
Saul Kahn, this is a subject that really is beyond Calc AB.
Oh.
It's not a subject that should even be worked on by Calc AB students.
Oh.
So
That's not my.
I get it about once every 4 or 5 years. I get a student that'll want to do problems like this delta epsilon.
I mean, it's not that I want to do it. It's just that it's on my
I
practice.
understand perfectly. It's just I'm not sure that I don't need a little review time to be able to do it.
Mhm.
And
Okay.
they want you to. Just because I do it so seldom. I've gone through it a couple of times, and
Mhm.
I can do it, but I need a little bit of advance notice.
That's okay. No problem.
Fortunately, if this is going to be on your test, uh,
Yeah, this is actually I don't actually know if this will be on my test because the thing is, this wasn't a practice test for for the section, but there's like a bunch of problems with this. Like literally all the problems have to do like all the problems that they've given have this delta
all right,
epsilon thing.
all right, all right.
So I don't know. But the thing is,
I
this is not in my
can do,
homework. So
I can go over an example problem in my calc textbook
okay,
that illustrates how this thing works. And
okay,
I think you'll understand why it's so complicated.
okay,
I can talk a little bit about the basic premise of it.
okay.
Okay, and let's just talk about the theory for a moment before we actually do problems. If I did a problem or two, I'm sure it'll refresh my memory. But delta is this distance right there between 3 and 3.4.
Okay.
So the distance between 3 and 2.6.
Uh-huh.
This distance is epsilon.
Okay.
Okay? And
Okay.
theory basically says that no matter how small of a delta you want to give me, you can
Mhm.
give me a delta of 0.01. Right now, delta is 0.4. But you can
Okay.
give me a delta as tiny as you want, and
Mhm.
I will always be able to find an epsilon that satisfies the definition of this thing.
Okay.
Even the definition I would have to look up. But that's essentially what it says. In other words, let's say you have a graph like this, a piecewise graph.
Mm-hmm.
Well, if you start thinking about it, let's call that 0.5.
Okay.
Let's call this 0.6.
Mm-hmm.
Let's call this 0.3. What is
Okay.
the limit of this function as x approaches 5?
As x approaches 5, it's 3.
Correct. It's 3 from the left, it's 3 from the right, but mathematically you can kind of see the problem here. In other words, if I know that it's 3, then I want to draw a delta around 3. And one thing is that no matter how close you want to get me to 3, I will be able to find an epsilon that is closer to 5, basically.
Okay.
It is very complicated and complex. And it really should not be taught to first.
Yeah, I don't actually. I just texted one of my a couple of my friends who were in my class, and they said that this probably won't be on the test because we never went over this.
I'll cover one of these if we have time towards the end of the session. I really think you'd be much better served by doing problems other than these.
Yeah. 1 second. Let me. So okay. So this is obviously they did not even talk about delta epsilon. So I don't know how.
This is the same thing. Yeah.
Yeah. All of them have to do with delta epsilon.
These are epsilon delta definitions.
Yeah.
Let's just try to cover some other stuff first.
Yeah. Can I send you a couple?
Yeah, absolutely. Go ahead and send whatever you want. You did mention you wanted to review some trig, that your trig was weak.
Yes. The thing is, I do want to review some trig, but I was wondering if we could do that maybe the next session, just because I want to be ready for tomorrow's test.
Okay.
I took a calculus readiness test in my class, and I didn't do so well. I got like a 63. Okay. So yeah, I really need to review my trig.
So standard limit problems, there's going to be some of those that are trig.
Yeah.
And you need to know, like that one we did yesterday, or day before yesterday, where it was cosine times tangent. Cosine of 8 theta times tangent of 8 theta all over theta. And you need to know that quotient identity. In other words, you need to know that tangent is sine over cosine.
Yeah. So the thing is, I know the most basic ones I do know. Okay. So like tangent theta is like sine over cosine, and I know like sine squared x plus cosine squared x equals 1.
Those are really the only ones you need to know. Okay.
Yeah, but the thing is, I have a lot of trouble like figuring out which ones to apply a lot of times.
Well, like on the one that we were dealing with, because we had a cosine and a tangent, then you don't want to change tangent into 1 over cotangent. You want to change it into sine over cosine so that we can reduce from 2 trig functions down to 1 trig function. So that's kind of what you need to use as a go-by in terms of which identities to use. There's the 6 reciprocal, there are the 2 quotient, and there are the 3 Pythagorean identities. And if you know those 11, that will get you through all of the limit problems you're going to have to do. And then the only other 2 things you really need to know is that the limit of sine x over x is, as x goes to 0, and what the limit of 1 minus cosine x over x is as x goes to 0.
0.
Correct.
Yeah.
Between
so I just sent you a couple of problems.
Okay. Yeah, those 13 trig things will get I'm sorry, did you say you sent me another file?
Yes, it just sent, so it might take a little while to
Okay. That
send
usually
like
takes
every like
10
yeah.
or 15 seconds after it says sent, but it has to say sent on your end.
Yeah, 1 second. Let me just check on my computer. Okay, it just sent. Oh, just kidding. I sent it to myself. 1 second. Let
Oh,
me forward it to you.
okay.
Um, okay.
I wonder if
Now it should be
I get a
sending.
lot of epsilon
We'll
delta
take a look.
problems. Like I said, for every
I
test
don't even know
problem,
why they gave that to us because it wasn't.
I don't either. There's no excuse for it if you want my honest opinion. It does nobody a service to have to deal with that. They're just they're demoralizing is what they are. I mean, you know, they're like the expert slope. The hardest problems in differential calculus are those epsilon delta. Without
Oh,
the hardest.
ugh, yikes. I don't know why they gave that to us.
I don't either.
Uh,
It really isn't
okay.
a
Yeah, so these are some of the problems that I really needed help with. Like, it was like I remember reading about LRAM and RRAM or whatever, but
okay.
uh,
That's left ram, middle ram, and right ram. And that has to do with integral calculus. They've already started you on that?
yeah.
All right. Let me illustrate to you on what they're doing here. Integral calculus, differential calculus is for the purpose of finding the instantaneous rate of change, which is the
Hmm.
slope of the tangent line.
Hmm.
Integral calculus is finding the area under a curve.
Hmm.
We have no way to find the area under that curve with
Hmm.
normal geometry. So the way calculus does it is it breaks it up into a bunch of rectangles.
Hmm.
And you can see that if I drew rectangles all the way here, I would get a fairly good approximation of what the area under the curve is.
Hmm.
But it
Yeah.
wouldn't be exact because I got that little area right there that's not under the
Yeah.
curve. And
Hmm.
this little area here. And then when I get over here, I'm going to have these areas here that aren't exact. And so
Yeah.
the secret to this is to make the rectangles as thin as possible. In other
Okay.
words, if I put a bunch of rectangles in there,
Yeah.
that's a
That
better
makes sense.
approximation.
Hmm.
And it will be. I mean, if we wanted to do an experiment, I could put like 10 rectangles under this area, and then I could go put 20, and then maybe 100. And you would find that the 100 rectangles would estimate the area the best.
Hmm.
And the limiting process is that you're going to add up the area of each of these rectangles, and you're going to let the number of rectangles go to infinity, which means the width of each rectangle is going to approach zero.
Hmm.
And when you do the calculus based on that limiting process, you get the exact area under the curve. It's no longer an approximation.
Okay.
Okay? And integral calculus, just so you know, is the inverse of differential calculus. And by that I mean the following. If y equals x cubed, we know that y prime equals, have you learned the power rule yet?
Um, no.
It's the easy way of doing derivatives.
Okay.
Start with the the exponent, multiply it by the coefficient, subtract 1 from the exponent.
Oh, wait, but the coefficient is 1.
Yes, 3 times 1 is 3.
Oh, okay, okay, okay.
Okay? If I had
Yeah.
the following, if I had 4x to the 5th, the derivative of that, I don't have to do it that hard way, the limit quotient definition. That's ridiculously hard. That's another thing they really shouldn't start calculus students on, is that. Okay? So here's the way to apply the power rule in a very, very easy manner of finding the first derivative. But what I mean by integral calculus is the derivative or the inverse. If I take the integral of 3x squared, it has to give me x cubed. In other words, if the derivative of x cubed is 3x squared, then the integral of 3x squared is x cubed.
Okay.
Okay? So it's like the antiderivative.
Okay. So, so
Sounds
the
simple
problem
enough,
that
it actually gets much harder than that.
mhm.
However, I'm getting a little ahead of myself here. Let's back up.
So
Talk about
yeah.
left ram, right ram, and mid ram.
So the thing is, they don't even talk about RAM per se. Like like the concept, they actually weren't trying to teach us about like left right angle approximation. So here, so it basically what they've given is they they gave us a bunch of rectangles, and then they gave us like y equals 5 over x, y equals 0, x equals 1, and x equals 5. And then they said use the rectangles to approximate the area bounded by those values that I just listed. So like if you see the problem, it's like it's not really our RAM, but it's like it's kind of like high level. So they don't really like
it is. They're just not calling it that. Okay.
Yeah.
So let's make a slightly easier function. Let's make, I'm going to demonstrate to you what exactly they mean here. Let's take this function right here. That is a parabola. Like that. Okay? Now, let's say I want the area from 0 to 4.
Okay.
I'm going to draw a line right there. I want all of this area that I don't know, now you can see me where I'm pointing. I want that area. Okay? Well, I've got a choice. If I'm going to draw rectangles, do I put the left side of my first, I'm going to put 4 rectangles in here. And I'm going to put them at 1, 2, 3, and 4. Okay? So there's one rectangle.
Okay.
Here's another rectangle. Now, notice the way I just drew it, I'm using the right side of these rectangles to intersect with the function. That's what they mean by right ram. If in blue, I'm going to go back and I'm going to use the left side. Notice the difference. They give you very different answers, but each technique is valid. In other words, the blue rectangles are going to underestimate the area under the curve.
Yeah.
The red rectangles are going to overestimate it.
And then you add those two and then you average it out to get like the answer.
That
right?
would give you the best answer, or you can even use mid. In other words, I could draw where that's going to be the top. Let me use a different color. And I'm going to make that rectangle right there all the way over at the midpoint. There's the midpoint of my next point. So that would be a better way to do it than either left ram or right ram. Notice that each of these rectangles has a little bit outside and a little bit inside. So they tend to balance another out. So the green is going to give you the best possible answer.
Yeah.
And the green is called mram, which stands for middle rectangular approximation method.
Mm-hmm.
The red is left ram, which stands for left-hand rectangular approximation method. And the right, or in this case, that was the blue, sorry, and the red is right ram.
Yeah.
Now, you might wonder, why are they even teaching this to you? Because this was the method that was used for thousands of years. Before Newton invented calculus, this is the way they had to do it. There were legitimate problems in the world where you had to find the area under the curve. This was the best they had, was by using rectangular approximations. And they would spend thousands of hours putting as many rectangles as they could, because I've only put 4 rectangles in here. If I were to put 8, I'd have a higher accuracy. If I were to put 100, higher still. And if I let the number of rectangles approach infinity, which means each of their width becomes approaching 0, I'll have the perfect answer. So that's why it's a calculus problem.
Okay, so if you look at the problem, I don't know how to do the problem that they gave us.
Unfortunately, it's so large that I don't know how to shrink it. Here, maybe we can figure out how. Can you send it as a file attachment?
Yeah, 1 second. Let me try it.
Yeah, and I can blow it up, or right now it's too big to really see on my computer screen.
Mm-hmm. Okay, 1 second.
Although we can talk about it for a moment. This triangle they're giving us right here?
Yeah.
You have any problems with that?
1 second. Let me send this to you really quickly, and then okay. So this is sending, and then meanwhile, let me look at the problem on my computer.
When you're dealing with straight lines,
so basically what they said,
solve it with geometry. You don't need calculus. Calculus is when you're doing.
The first one was pretty easy because that was just obviously the height was 4 and the base was 5, so you could just do 20 divided by 2 is 10.
Correct. You don't need calculus.
But then if you move to the right, like if you move to the right of the problem, it was like a curve, and then it was kind of like
Okay.
Yeah. So it was that, and then I don't know how I got that answer. I don't know how to get because in this problem I said the answer was 7, and it said the problem seems to require calculus. Find an approximation of the shaded region by using a graphical approach. Treat the shaded region as approximately equivalent to a triangle on top of a rectangle, and sum the areas of the objects.
Okay. Not quite sure what they meant by that last, but I assume they mean this.
I think they meant to like draw like kind of like a horizontal line at at y equals -3, and then
that's what I'm thinking. Also, is they want you to figure out the area of that rectangle, and then they're going to assume that we're going to put a triangle there.
Yeah, and the height would be 1 of that triangle.
That matches that curvature pretty good. So what's the area of this part?
6.
What's the area of this triangle?
It would probably be 1 because the height is like approximately 1, and like the base is 2, so it would be 1 times 2 divided by 1, which is 2 divided by 2, which is.
So a good approximation for that would be 7. Okay. Yeah. That's not really the way they do it, though. They do it by drawing rectangles. In other words, maybe I would put 4 rectangles in there. Okay? So I would do it like this. And then I would just figure out the area of each rectangle. Now, figuring out the area of these rectangles is not hard when they've labeled everything for us. But if you're doing it from a calculus point of view, then this point, in other words, if I want to figure out the area of rectangle number 1, What is it? It's its width, which is 1/2, times its height. Well, what if its height is f of minus 1.5? That's the notation you got to get used to with calculus. Is you don't need to put a height on there. I don't need this height right here. I'm just going to call it f of 1.5 because that's what that is. That point right there is f of minus 1.5. So the height of that rectangle is f of minus 1.5. The height of rectangle number 2 is f of minus 1. Exactly.
Minus 1, yeah. Okay. And then it would be minus 0.5.
The other one is minus 1/2. And it depends on whether you're using right rectangles or left rectangles. In other words, in the case I just went through, this would be the right ram method.
Yeah, and if it was the left ram, it would be -2, -1.5, and -1.
The first one would be f of minus 2 instead of f of minus 1.5.
Yeah.
And if you had 8 rectangles instead of 4, then their width would each be 1/4. And then you just add them all up. It's a summation process. And that summation process can be described using sigma. And sigma is the Greek for the integral sign. So that's the way you would do problems like that.
Okay. So,
depending on how many rectangles they tell you to, if they said use 6 rectangles, then these points are going to be different. Okay. Now,
okay.
Is there anything
Next
else?
problem, there's another one. So
let me back up here and see if I can get one that I can resize. Yeah, as an attached file. Actually, I think is all I have to do is, I don't think that's the way I want to do it, but that's probably not the way I want to do it. I want to do it this way. And if I just click on it, this is a better way for me to do it. Now,
so it says the region is bounded by y equals 5 over x, y equals 0, x equals 1, and x equals 5. And then somehow I got this answer, but I don't know. I honestly don't know how.
Okay, well, tell me on this method right here, tell me if that's left ram or right ram.
For the first one?
One on the left, yeah.
Yeah, that's left ram, I think.
Left ram, because the left corner of that rectangle intersects the function there. This is also left ram. The only difference in these is the one on the right uses twice as many rectangles. And if you go through the math, it'll be the more accurate one. Notice the one on the left is going to overestimate this area by a lot. You got all that area there, there, and there. This one, not so much. You still got this area here and this area here, so it's still going to be overestimated. But it's
more accurate than the first one.
Yeah, it's definitely going to be. Now, in terms of this, that clearly is our function, y equal 5 over x. It's a hyperbolic function. And they didn't put the other half of it. The other half of it would go here. Because their boundaries were y equals 0. That's right there. And
then y
equal 1. That's right there. And x equal 5. So the function is bounded by the function and those 3 straight lines.
Yeah.
All right, so let's see what their questions say here. Describe how you could continue this process to obtain a more accurate approximation.
So that's not even the problem that I'm like really worried about. It's just the part where it says use the rectangles to approximate the area bounded by those sections.
Okay.
Yeah, I just didn't know how to use those boundaries to get the area.
Should we start on 1 or 2 to do that?
1.
Okay. Here's what you're going to do. The width of each rectangle is 1, correct?
Yeah.
So we're going to sum up. We're going to sum. the area of rectangle 1, and the area of rectangle 1 is its width times its height. And in this case, its height is 5.
Mm-hmm.
Right? Right there.
Mm-hmm.
Plus, the second rectangle has a width of 1, and its height is about 2.5.
Mm-hmm.
Third rectangle has a height of about 1.75.
Oh, okay.
And the fourth rectangle has a height of about 1.25.
Uh-huh.
But that's not really the way you do it in calculus. What you do is you call this f of 1. In other words, it's really 1 times f of 1.
Mm-hmm.
And then you just substitute. You're given the function usually. Well, what's f of 1? It's 5.
Yeah.
What's f of 2? It's 5 halves. So
Mm-hmm.
that was a good approximation. F of 3 is 5 thirds.
Mm-hmm.
5 thirds. And f of 4
is 5/4.
Yeah, it's 5/4 exactly, which was 1.25. So,
Mm-hmm. Yeah.
but that's the way you do it, and this is the very beginning way they teach you how to do it. But the real thing you have to realize is that this is f of 1.
Mm-hmm.
As opposed to a number. Now, if you want to figure out what f of 1 is, as long as they give you the function, you can plug in x for 1 and you get 5.
Mm-hmm.
Okay? All right. What next? Now, the
So
second one,
I just didn't know how they got.
this is just 1/2.
Mm-hmm.
But these points, you're going to plug in that point for x, so it's 5 on the height of that first rectangle, still 5. Height of the second rectangle, you're going to plug in 1.5.
Mm-hmm.
It's 5 divided by 1.5. That's what the height of the second one is, and so forth and so on. Does that explain it better?
Yes. So the next thing I had trouble with really, okay, so the I don't know if you could go back to my last email. It was like a problem that had to do with secant lines. Um, one second. Yeah, if you could just
I can
go back.
Okay. Go back to the email before this, which probably this one.
Yeah. No, 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 the one before that.
One before that. Okay. I know what you're talking about, and I can show you how to the limiting process on a secant line.
Yeah, I know this is kind of the picture thing is kind of
It'd be
annoying.
easier if I explain it. You tell
Okay.
me, okay? Because I've explained this so many times that I think I can do a good job. Hold on a second.
Oh.
If you want the slope of the tangent line at that point right there, we're going to call that point x. What does that make this point right here?
Why?
F of x.
Oh. Yeah.
Okay. Now we're going to put a secant line in there. And we know how to figure out the slope of that secant line. And the right-hand point on that secant line, this distance is h.
Okay, okay, okay.
So this is x plus h. With me?
Oh, okay, 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 yeah.
What that makes that is f of x plus h, correct? What's the slope of that secant line?
It's gonna be f of x plus h minus f of x all over. Well, it would be x plus h over minus x, but that would just be over x.
Over
I
h.
mean over h. Oh wait, that makes them. Oh, that's how you find it.
That's
Oh
what
my
the
God.
definition of derivative is.
Okay,
Is if you want the slope of the line right there, then what you do is you keep reducing the distance of h, which brings this point down the curve and creates a series. In other words, as h gets smaller and smaller and smaller, the limit of that secant line slope matches the slope of the tangent line. And that's where that definition comes from. In other words, we're going to take the limit of those as h goes to 0. And that will give us, because we have no way of figuring out the slope of the tangent line. Slope is rise over run. We can figure out the slope of the secant line. We have an average rise and we have a run. So we can divide the rise by the run. And the calculus, this was the very beginning discovery of calculus, is taking this secant line, letting h go to 0, and you end up with a tangent line. And that's how you figure out the slope of the tangent line. So whatever this function is, you plug it into this formula and you solve it as a limit problem. And that gives you the first derivative.
Okay, so for this you would plug, okay, but technically it's x as x approaches 0, so wouldn't this be undefined because h on the bottom, if you do direct substitution? Oh, that's when you would use factoring or whatever.
Absolutely. It's not going to be undefined. Notice that I can see that there's a slope there that is defined.
Yeah.
And never forget that first derivative means slope. That's what it means. When they're talking word problems and they use derivative, first derivative, they mean the rate of change. What is the instantaneous rate of change? When you're in a car and you're going 40 miles an hour, that's a first derivative.
Yeah.
If you accelerate, that's a second derivative. But your first derivative is miles per hour. That is a rate of change, and it is instantaneous. In other words, your speedometer is saying 40 miles an hour, but if you press on the gas pedal, it'll say 50 miles an hour 2 seconds from now. So the instantaneous rate of change changes depending on what the velocity does. And so that's the secant line, is the average rate of change, and the slope of the tangent line is the instantaneous rate of change at point x. Now, does that help with that problem, or do we need to bring that problem up?
No, it's okay. I think I understand it. Can we just do the problem?
We did this curve I drew here. Let's call it x squared.
Okay.
Okay. So if I want to find out what the rate of change at point x is, I'm going to use this formula, which is x plus h squared minus x squared all over h. If I do the math, this will come out to be 2x. And notice that if I use the power rule, I take 2, multiply it by 1, subtract 1 from 2, and I get the 2x a lot easier. They will teach you the power rule. That's the way calculus should be started, is to teach you the power rule.
I just noticed. Okay, so x squared, the 2 minus 1 becomes the exponent, and then 2 times the coefficient, which is 1, is 2.
Exactly. And that's the power rule. Next comes the product rule. When you're multiplying two functions together, it's not just the derivative of one times the derivative of the other. It's a more complicated procedure. Quotient's a little more complicated still. And when you have composite functions, you need to use the chain rule. But between those 4 rules, you will never again have to use this rule. Seriously, they won't ask you to do it ever again. They're going to try to demoralize enough calculus students to get them to drop the course if they can't get by this. But there's no reason to teach calculus that way. There's a real easy way to take derivatives, no matter how complicated the function is.
Yeah.
You've got to memorize those 4 rules. And those rules are easy. Those rules are so much easier than doing it by this f of x plus h method.
Yeah.
That's always hard algebra. There's hard factors, hard algebra,
And if you go wrong somewhere, then your entire answer
Oh,
runs away.
yeah. Whereas the power rule, you can't. I mean, just take this function here. If I have to use this method, man, I got 1 over x plus h minus 1 over x, all that hard calculus. But if I just express it like this and apply the power rule, first derivative is what? Of x
Um,
minus 1.
it would the first derivative would be would it be negative x to the wait, it would be negative 1 over x squared.
Actually, that's right, which I've written this way.
Yeah,
In
yeah.
other words, calculus works a little bit better if you use negative exponents
Yeah, okay, okay.
than leaving the variable in the denominator. In other
Yeah.
words, you don't need to put it back into negative 1 over x squared. But you can see we get the answer in about 3 seconds doing it the easy way, and
Yeah,
we'd still
that's
be working on it if we had to do it the hard way.
okay. So the problem that I sent you, like the secant line problem, I just want to make sure I know how to do it with someone like watching me like do it.
Okay?
So let's see if I can well, I'll pull that problem up on my computer as well so I can follow
I
along.
think the only one
Okay.
I have maybe is the one that's too big to see.
Okay, wait. If you scroll down a little bit, just
And
a little bit more, yeah, it's not this, yeah, so w way more. I think it's one of the first, like it's at the very bottom.
okay, of this page.
Yeah, yeah, yeah.
Okay, there's the bottom. Let me
Oh
scroll.
no, there's more. There's more pictures.
Oh, oh yeah, really bottom. Okay, yeah.
Yeah. So yeah, so
Not
not
those
this one, but
three. We did
yeah.
that already.
Mhm. And then I
Probably
think it might
too low.
be it
Oh,
might be
maybe
yeah, I think it was this one.
this one right here,
Yeah.
the straight line one.
I hold on. Let me see if I can. Let me open that problem up on my phone as well. Okay, yeah. So this one.
So
Um.
what do they
Oh,
want?
actually, this is not. Sorry, this is not the problem. This is
No, I didn't
the.
think so. This is actually you don't even need calculus on this. That's
Yeah,
straight
you
lines.
don't. You
You use geometry.
don't. So actually, I think it was a problem right after that. Yeah. If you scroll down a little bit, I'm not sure. Oh, I don't think it's sent. Let me send it again.
Send it again as an attached file, and then I'll be able to
Yeah.
be able to.
Okay, that's really weird. It's not letting me send this.
Oh,
Just give me a second, 1 second. It's not letting me send this, so I have
okay.
to pull it up on a different. I have to take a picture again, really quick. Just give me one quick second.
Sure.
Okay, and then I also wanted some help on this problem.
Okay. Can you verbalize it, or
Yeah, I
I
can
mean, you
verbalize
might
this
be
one.
able to.
So this
If you
one is
can verbalize it, go ahead, and I'll just write it out.
okay. So this one isn't about secant lines. It's just about solving limits analytically, or like just solving limits. So it's a trig limit problem. So it's limit as x approaches pi over 2. 3 cosine x over cotangent x.
3 cosine x over.
Over cotangent, yeah.
Okay. So obviously, if we plug in pi over 2, cosine of pi over 2 is 0. Cotangent of pi over 2 is
That would be also 0.
also 0. So we got
But
0
then that
for
would
0.
make it undefined, so.
Okay. So let's use our trig identities to try to turn this into a single trig function.
So this would be
Okay.
cosine squared. It would be
Cosine
it would just be
over
sine x. It
sine.
would be sine x.
Yeah. So this
Yeah, okay.
thing turns into 3 sine x,
Sine okay.
and sine of pi over 2 is 1.
Is 1. Okay.
This would
Okay, yeah.
okay.
Okay.
So that's
That
where
makes
you need these basic trig identities.
mm-hmm.
And
Let me
the reason I chose the quotient one is because if I choose the 1 over tangent, it doesn't really progress the problem. I'm
mm-hmm.
trying to turn it into one trig function, not just a different two trig functions.
Yeah. So here's another problem that I needed help on. So it's limit as x approaches 0, sine to the power of 6x over x.
I remember seeing this on your thing. All right. We can write this as sine to the 5th x times sine x
Over x,
over
right?
x, and we know what that goes to.
That's 1.
Okay, what's this go to?
Sine to the, okay, well, that would just be 0.
Yep, so that's the answer.
Oh, 0 is the answer. Okay.
Mm-hmm.
Oh, that's not too bad.
Yeah, it doesn't always have to be a number. It can certainly go to 0.
So this one, the next one is
The secret on these trig is to always try to pull out a sine x over x. It
over
doesn't
x.
have to be
Yeah.
sine x over x. It can be sine of 8x, as long as it's 8x there. That is 1.
Yeah. Okay. So, okay. Yeah, that makes sense. Okay, so I had another question. So this one is, limit x as x approaches 0, sine x over 3x.
Okay. Again, I want to multiply or
By 3 over
divide both sides. I want to multiply both top and bottom by 1/3.
Okay.
That's the easiest way to look at it, I think.
So that we can bring it to an x on the
Now I
bottom.
got 1/3 sine x over x. That goes to 1, so the whole thing goes to 1/3.
How did you get, oh, ooh, okay.
In other words,
So my teacher, the way
can't
the
say
the way
it
the
goes to 1 unless that is the same as that. So in order to get that to be the same as that, I multiplied the top by 1/3 and the bottom by 1/3.
but when you multiply the top and bottom by 1/3, so if you multiply the top by 1/3, you'd get sine 1 over 3x.
No,
And then
you don't. No, you don't. You get 1/3 sine x.
oh, right. And then okay, and then you would on the bottom you'd get you'd just get 1x.
Exactly. Which
Okay.
I've got the magic thing that I'm looking for right there.
Okay.
That's
And
the
the way
secret
that
to all
teacher
these trig limit problems. It's just to be able to pull out a sine x over x, or the other one, 1 minus cosine x over x, and you'll notice that it also works the other way. Cosine x minus 1 over x. Both of these limits are 0.
okay. Cosine x minus 1 over x.
Or 1
Also,
minus cosine x over x. They
do you
both
mind giving me a
start
problem like a
out 0 over 0, but
Mhm.
the true limit of each of them is 0.
Okay. So, do you mind giving me a problem for the cosine x one? Just like a problem where I have to simplify it to get to 1 minus cosine x or cosine x.
I don't know if I can make one up. I can find one, I think, in the book. Yeah, let me see if I can find some of these that are going to use cosine. That particular one. And the way it generally is written is 1 minus cosine x over x.
Mm-hmm.
Even though it's also true cosine x minus 1. And their problems at the back. Let's see. What is x cosine x? I'm trying to think if that's one of them. If I have x cosine x, and I take the limit as x goes to 0. What's that? Just do
Okay.
substitution.
Yeah, so then it would just be 0 times, I mean, cosine 0 is just
1.
1. But it would, anyways, you're multiplying by 0, so it'll just be 0.
Yes.
Okay.
Okay. Oddly enough, they don't have a lot in here. I can't see a single one in the book that requires you to use that cosine or 1 minus cosine.
Yeah, there weren't any in my homework too, but I'm really, so my teacher, he has like a tendency to like, I don't know, he's a really harsh grader, and he really likes everything to be written out like perfectly, and so it's just like, I don't know.
Okay, here's one. This is pretty simple. I'll try to find a little bit harder one, but
this is just 0, 2, right?
correct. In other words, what you're trying to pull out is this. We know what that limit is.
That's 0.
0, so whether it's multiplied by 3 or some other number, it's still going to be 0. See if I can find a different one.
So, really quickly, I just wanted to go over something with you as well. So, the one thing my teacher, like, kind of taught us was, okay, so you know the problem I gave before, which was limit x as x approaches 0, sine x over 3x?
Yeah.
So, the way he, like, kind of explained it to us, which I didn't really get too much, was, so if it was sine x over 3x, or let me show the problem that he gave us as an example in our notes was sine 3t over sine 2t.
I was going to say, it's a little easier to understand when you do it like this.
Yeah. So and then he multiplied both numerator and denominator by 3.
3.
And then he pulled,
And
so
now,
he had.
Now you have that magic expression.
Yeah, and then he just multiplied the so that would be 1, and then you just multiply.
Exactly.
Okay.
It's just a question of always pulling out something that you can say the limit is 1, or if it's cosine, it's 0. I do have a little bit of a harder one here. Let's see if we can tackle this one.
Okay.
1 minus tan of x all over sine x minus cosine of x. And we want this as x goes to pi over 4.
Okay. So first I would try direct substitution, right?
Yeah, and actually I think that might work. That actually, yeah, this is tan of pi over 4 is 1, so it's going to be 0 on the top. And sine of pi over 4 is the same as the cosine, so it's definitely 0 over 0.
Yeah, and that would be undefined, right?
No. Remember, with limits, that just makes it a hard limit problem. It's not undefined. If it's a number divided by 0, that is undefined. But
right. Usually it's 0 to 0 problems that they ask.
You can probably use trig function or trig identities. I'm going to turn everything into sine over cosine.
Yeah, so this would be 1 minus sine over cosine x. Okay.
All over sine x minus cosine x.
Mm-hmm.
Okay, common denominator would be cosine. So this would be
cosine x minus
sine over cosine all over sine minus cosine. Yeah. If I flip and multiply, cosine minus sine divided by sine minus cosine is minus 1.
Mm-hmm. Yeah.
A minus b divided by b minus a is always negative 1.
Okay.
So this whole thing becomes minus 1 over cosine.
Cosine, which is negative secant.
Well, we don't even need that. Now we just need to go back and resubstitute.
Oh, right. It's just
cosine of pi over 4 is root 2 over 2.
2, yeah.
So it becomes
and that would be
minus
negative 2 over root 2.
Right, which I don't know how your trig teacher taught you, but
yeah, if you want to, you can multiply it.
The new trend in trig is to not rationalize the denominator for obvious
Yeah.
reasons
My
because
teacher said that as well, which was just don't if you have a answer and it's technically correct, don't do more like don't do more to it
in other
because
words, this
you're
is
setting
the
yourself
same
for
number as this is. They are not different numbers. The only reason we normally express it like that is because we don't like having irrational denominators. But
Yeah.
in trig, they don't pay attention to that because you got all your reciprocal functions. In other words, if the sine is 1 over root 2, that means the cosecant is root 2 over 1.
hmm
And so
hmm
rationalizing it can kind of be a self-defeating purpose. So they tell you just not to rationalize.
Okay. So I had just like maybe one more question. This one was about the secant line, which I didn't get to before. So
We got 5 minutes. I'm willing to do one epsilon delta one that's in my book if you want.
actually I don't want to confuse myself now
Okay.
just because
All
I
right.
talked to a bunch of
Good
people
idea.
and I
Good idea.
emailed my teacher and he said there's no delta epsilon.
Okay.
So I don't know why this textbook, this web assigned thing decided to put that on the practice test.
You'll be happy
We
to know that the AP Calc test does not test you on epsilon delta.
Okay, that's good. Okay, good.
There's a lot of things
Um,
they'll teach you in calculus that go beyond what's being tested on in the AP Calc, which is senseless. Calculus is hard enough as it is. You don't need to make it harder.
yeah. Um, this is another problem that I had trouble with. Okay, so I'm gonna try my best to take pictures and send it as quick as I can. Okay. It's a two. I had to take two pictures because it didn't fit on one computer screen. So, like the one part of my computer screen. So,
Okay.
let me send you both.
We can still handle it, I think.
Okay, it's sending.
Okay. Turns out when you're sending attached pictures, try to only attach one or two at a time. If you attach like 4 or 5, it takes forever for the
Yeah,
to get there. It's like exponentially longer.
yeah,
So
yeah.
if
Okay,
you send
it got
one,
sent.
it gives us something to work on. This page?
Yeah. So this is graph F, and the secant lines passing through the point 4, comma 2, and x, comma f of x for x values 3, 5, and 8. So obviously, the graph would be the fourth one because x square root of x that's just like the function. But then after that, how would I find the slope of each secant line?
Well, we have the function, right? Graph F and the secant lines passing through the point for x values of 3, 5, and 8. Okay. Well, is this a multiple choice? We're supposed to pick one of these?
Yeah. So I picked the right one. I mean, I think I know
This is
why.
the only one that is the graph of square root of x.
Exactly. Yeah.
And
If you go to the next picture, you'll see the
reflection.
bottom part of the problem.
What's that?
If you go to the next picture,
Yeah,
yeah,
yeah.
you'll see the bottom part of the problem.
Okay.
Yeah.
I think I can just do this now.
Yeah.
Okay. Find the slope of each secant line. All right.
Would I just do the change in y over change in x over change in y over change in
Yes.
x?
Secant lines are not calculus.
Okay.
Secant
Okay.
lines are geometry.
So only for tangent lines you would do the f of x plus 8.
Yeah. What were the numbers that it was supposed to pass through?
So it was supposed to pass through the point 4, comma 2, and then 3, comma f of x. And f of x would just be square root 3.
Okay.
So it would be square root 3 minus 2 all over 3 minus 4.
Yes. In other words, so it passes through that point right there.
Mm-hmm.
And it also passes through which of these, what's the x-intercept?
A 3, comma square root 3. Oh, that's not the x-intercept. That's just the point that they want us to find um, slope of.
Okay, so this point right here is what?
3 comma square root 3.
Okay. And this point is 5 comma square root of 5. And this point is 8 comma square root of 8. Now, the only thing I'm a little puzzled at is that they've got these passing through those negative. The x-intercepts are negative. Find the slope of each secant line. Okay.
Oh, I think I understand it.
The only
So
thing
you would
we
just
need is the rise and the run, right?
yeah, so you would just do square root 3 minus 2, which is negative 0.268 divided by negative 1 because it's 3 minus 4, and then you'd get 0.268.
You got it. Exactly.
Okay, but then how would I do number C, part C, which is to estimate the slope of the tangent line?
Well, the slope of the tangent line is going to be the secant line that most resembles a tangent line. Now, unfortunately, the way they've drawn it here, you can't really, all of those secant lines look like slopes of the tangent line to me.
Yeah.
So, use the results of part B to estimate the slope of the tangent line.
I think you're supposed to add all 3 of these up and divide by 3. I'm not sure.
Well, yeah.
That does not yield the correct answer.
So the slope is square root of 3. So the rise is square root of 3 minus 2 over the run, which is 3 minus 2, correct?
Mm-hmm.
So that's the first slope, right?
Yeah.
And each one would be done the same way. Only the second one is going to be square root of 5 minus, oh, actually this is 4.
Yeah, I'm a little bit puzzled by this as well.
Yeah, I am too. Let's see. We know that it passes through the point, the function is q. No, what is q? The q is 2 or 4 comma 2?
Yeah, no, Q is just any other point on the line.
Any other point on the line is, so the first q is 3 comma square root of 3. Okay, now I got it. Okay, so I understand B.
Mm-hmm.
So we're not going to take the average slope. We want the slope of the line that is the most tangent. It's not, it's really hard for me to see what they're trying to get at with that picture.
Yeah, me too.
Because those all look like tangent lines. In other words, in the drawing that I drew for you earlier, there's the secant line right there, okay? And there's the point where you want the slope.
Mm-hmm.
Well, the way you get that slope, if you have multiple secant lines, then this would most closely approximate the slope of the tangent line.
Yeah, so the thing is, I don't even think like if I were to do this like algebraically, I would just use square root. I would do the x plus the difference quotient, right?
Yeah, exactly. In other words, you're
So
going
I
to
would
do
do
f of
square root
you're going
4 plus.
You're gonna do,
H.
you're gonna do square root of x plus h
Yeah.
minus square root of x all over
Yeah.
h, and you're going to find that limit as h goes to 0. The thing is
Yeah.
I'm not sure how we apply that to these problems because we can't see what h is.
Yeah.
However, let me think about this for a second. Clearly the point 4 comma 2 is on that curve. And so that's what they want. Now, I can tell you if the function is square root of x, well, then the slope of that tangent line is 1/2 x to the minus 1/2. And we're trying to find the slope when x is 4. So it's 1/2 divided by the square root of 4, which is 1/4. So the slope of that secant line that goes right through here, in other words, the tangent line, is 1/4. How we get it by doing this method, I'm not sure. I can't quite see where they're going with that. You can kind of see we're getting closer to 1/4. And then down here, it's even closer to 1/4. The true slope of the tangent line is 1/4. Just doing it the easy calculus way.
One second. This just okay.
I guess if we do that calculation, we do probably get 2.68, right?
Yeah. So hold on. Let me just plug
And
this
then we
in.
get 2.36, but then we're moving away from 1/4. That's because that secant line right there is closer to the tangent line than the other two secant lines. In other words, if you look at the slopes of these second two secant lines, they're not 1/4. They're moving further away from 1/4. And yet we know that the slope at the point x equal 4, it's halfway between 3 and 5. That's the way you do it.
Oh, right. That makes sense.
That number is exactly halfway between two numbers.
Yeah.
You add those two numbers, because 4 is halfway between 3 and 5.
Yeah, that makes sense. If you average those two out, you get
there. We don't really need the 8, but no, that'd be the way to do it, the way they're wanting you to do it here.
Yeah, okay, that makes sense. All right.
Yeah, that's a strange way to explain it, but...
Yeah, but even if you do the power rule that you showed, it would be 1/2 times 4 to the power of -1/2, which is just 0.25, which is technically the right answer. This is just
exactly. The exact answer is 0.25. The way they got 0.252 was just to add those two numbers and divide by 2.
Yeah, technically that's not even as accurate as it would be to do.
That's right. That's right. Yeah. Taking the average secant line is never, that's kind of like using rectangles to approximate area under a curve. It's never going to get an accurate answer. And to get an accurate answer, you've got to use calculus.
Okay. Sorry, I have got to run. I have a piano class.
Yeah,
so thank you so much for all your help.
I apologize for that. But good luck on your test. I hope I've helped you. And
yeah, you did a lot. Thank you.
If you ever want to cover the epsilon delta, just give me a little, like, the day of the session. Yeah. Tell me that's what we're going to cover, and I'll be prepared.
Okay, perfect. Okay? Thank you so much.
You're welcome. Talk to you later.
All right, bye.
Bye-bye.
See you.